Welcome to Advantest Talks Semi. Several industry sources have the semiconductor industry revenues growing to a staggering $1 trillion within the next decade, essentially doubling in size. Join Marc Hutner, Senior Director of Product Marketing at proteanTecs, and I as we discuss how AI and machine learning technologies being adopted across the semiconductor test ecosystem are essential to achieving the $1 trillion target. Before we get started, here's some important news from Hera. Hello, Hera.
Hi, Keith. I am very excited to give everyone updates on our annual Voice conference. We will be hosting Voice in person this year in Scottsdale, Arizona, from May 17 to 18. After hosting this event virtually last year, we can't wait to get back together with a bigger and better conference. Everything from amazing keynote speakers, technical presentations, sponsor booths, and of course, raffles and prizes you won't want to miss. Our registration is now officially open, so you can register at voice.advantest.com. Again, that is voice.advantest.com. We can't wait to see everyone under the hot Arizona sun. And as always, be sure to connect with Advantest on Twitter, Facebook, and LinkedIn for all the news and much more. Keith, that's the latest. Back to you.
Thanks, Hera. We're going to talk about semiconductor analytics, AI and machine learning, big data, all these new hot topics that are important and driving the era 4 of the semiconductor industry. Era 3 was $585 billion last year, and we're slated to achieve the $1 trillion mark in around 2031 or 2032. And the major portion of that growth is coming from AI and machine learning. Because if we look back 25 years ago, the focus was on the technology, making the measurement, and the data was sort of an afterthought. The data was just something that was used to decide pass or fail. Now, here we are 30 years later, the data is king. The data is the most important. And just want to understand your perspective on this. What's some of your experiences?
Yeah, I think you're absolutely right in terms of your experience. You know, I joined the industry back in the late 90s, where I was an instrument designer for test. And it was definitely make a good measurement and consider each test as a unique event. So how do I get to a spec limit? It was a real focus of the industry. And now I think we're up to hundreds of thousands or maybe even as high as a million tests on a part. And now you're really getting into the how can I optimize that and look across tests, I think is a big trend that is really turned it on its head for our industry in general. Because I think there is a lot more than the single spec. I think it's really the looking across specs and then doing an optimization has become very, very important. And if you kind of look back, you know, when we started this, we logged these things into text files and put them into simple databases. And then ultimately in the 90s, we moved into this domain of STDFs and binaries. And now we're even moving it one step forward with a couple of the new test standards where it's getting to streaming test standards like RITDB or TEMS. And it's really become like the immediacy of the data before we could get away with things like looking at the data after the whole lot was tested. Now we're really looking at as it's coming off the tester and making in situ decisions. So I think the way that we're thinking about data and at test is changing quite a bit.
Yeah, that's some good insight, Mark. I guess the key takeaway for me is that there's just tremendous value now there with the data. So somehow collecting this data, because it's all valuable, and utilizing it, we're just scratching the surface of what's possible.
Yeah, and I think sort of the test techniques to collect the data has also been changing quite a bit. So, you know, if you kind of look back where we started, it was only possible to do that test on the tester. And where we're moving is, you know, this common sort of test technique can be applied at any stage, including the field. Now you got this great possibility for correlation, which wasn't easy or possible before. It's very exciting.
It feels to me that a lot of the data analytics and the data analysis that we're doing in industry, a lot of it is still very manual. And so I suspect that it's quite tedious and difficult to extract the value. Have you experienced the same thing?
Yeah, and I think that's the next part of the revolution that's going to occur is how do you make it so that way it's easy to come to some kind of conclusion or insight. Like with the instruments, each of these measurements are very, very specific to a situation. So how do you get that situational information and then apply it to multiple phases? So we'll need to do that as an industry to make that really getting value from the data itself will be a real big challenge for us.
So speaking of the value, what are some of the low-hanging fruits that you see that maybe customers are already doing, but maybe some others that they're not doing that they could be doing?
In terms of low-hanging fruits, it's really understanding what's changing on the die itself over its lifetime. So where it started versus where it is and where it's going to be, I think is really an interesting problem. And, so for something like automotive or data center, it'll be vitally important. So how do I predict when to do a maintenance cycle is going to be extremely important because it ends up optimizing your maintenance cost of the vehicle or the data center. And I think that there's a lot of technologies that can be brought together, including analytics, to analyze the health. So it does really start with reliability testing and, early ramp and characterization testing. But how do I build those models to really understand, once I ramp a product, how healthy it is over its lifetime?
For the benefit of the audience that maybe is somewhat new to machine learning, talk about machine learning, how these models work, how a prediction actually can come to pass, and how it can be extremely accurate if the correct data and feature sets are chosen.
Yeah, sure. The machine learning today is really based off of trained models. So it's how do I take a set of historical data and then ask it the questions about, can I see a particular fault or a fault type? And then what occurs as you kind of apply that data. So you have to groom it a little bit to sort of have the right input features so you know why you took a particular kind of measurement. And then what do I want to learn from that data? And then you're passing it through basically a neural network. The idea is that you've created a model that has an understandable input-output relationship. So the tricky part is really saying what are the input features that you want to consider to then lead to a prediction of an action. So, and that's actually where the bulk of the work is for a machine learning model.
Like you said, selecting that feature set is really important. And there are thousands of features, maybe tens of thousands of features. Sony did is they figured out some feature sets from parametric test. And I bring that up because this is why it's so important to have the data ports or the data portals connected. So they had some feature sets from parametric test data, and you can pair them or marry them with the test data during the in situ test, and you can make some predictions. So one of the things that was in the paper was with frequency test. And so you could actually predict what the result is going to be before you even made the measurement because you have access to this data from parametric test, right? So I've predicted that I'm going to measure 10 and I measure 9.8. Then I'm pretty sure that my measurement result is accurate. But if I predict that I'm going to measure 10 and I measure 5, well, something's gone awry. Either the measurement equipment needs to be recalibrated, maybe the process is drifting, or maybe my model is getting old and it needs to be trained. But in all cases, something has gone awry and I want to know about it before I pass that device or fail that device.
The tricky part is really what do you want to learn? So, proteanTecs itself has a lot of these kinds of parameters that we measure, and one of them is a predicted leakage. We look at different process parameters that we can measure across the die and then do a prediction of what the aggregate on the die will do. That will end up saving a lot of time because it would have caused you to do a lot more kinds of measurements. So there's a lot of things that we can do with a model, but I think the difference in how we're thinking about it is we start with what does the model need to do a certain kind of prediction, and then we're generating certain on-die features. And I think that's part of the next revolution is how do you optimize the kinds of data that you are collecting, because it's not an afterthought. It goes back to your, data as an afterthought versus an ML first or a prediction first mindset.
One of the things that the industry is seeing is the challenges of deployment. So our industry is very much risk averse. Basically, Mark, why is our industry so risk averse?
Well, I think it comes back to the measurement thought of how do I predictably do something, right? I want to make sure I can guarantee a spec. And anything about changing a setup, people get very nervous. So if I've been developing on a 93K for the last 5 years, I have a certain configuration. Folks like to keep with that configuration because all their processes have to do with that setup and that mindset and that training of people. I think that even though folks are risk averse, they tend to find areas that, I'm developing the next 5G thing. And then they say stuff like, there is no measurement technique to do it this way. So it's really where should I take risk and where does it make the most sense? But we always tend to go back to tried and true methods is kind of what it comes back to. Is if it's possible to get you back to a known method, we tend to go there because we don't want to risk our product ramp against something that's unknown because there's enough moving parts. Like if you consider 100,000 test numbers, you don't want to make everyone risky. You only want the ones that really have to be risky.
Yeah, that's a good point. And it reminded me of, once we get something released into production, first of all, to get it released to production is a huge task. So once you get it released, you don't want to change it because if you do change it, you have to go through that entire process again.
Yeah, and I think this is also where ML has a bit of a challenge being accepted because it comes back to the explainability of a decision. So if you can have a method that changes limits around or gives a prediction, it's not only doing the prediction. I think it's vitally important to understand why it made a decision and how the model is changing if you're allowing for a real learning model. So I think that there's several challenges in our industry of accepting this as a new technology, but I think that there's also a great opportunity associated with it. So I think this is one area where we'll find that there are really thought leaders that are driving it, that see this as a huge opportunity. The rest of the market will follow suit once they have that proof point. Not sure if you read a really good book called The Innovator's Dilemma, but that one had a fantastic model of early adopters versus the mid-market and then the late adopters.
Well, speaking of early adopters, I was thinking about how to accelerate AI because again, we're talking about 500 billion growth over the next 10 years, and every company wants their share of that. And so the question I pose to customers and suppliers is, how are you going to get your share of that? And really find the AI opportunities with the highest ROI. But tomorrow's AI leaders are setting those strategies. They're organizing to start with low risk and high return pilot programs. But for the long term, they have to have a strategy that aligns with the business strategy. And I get back to, okay, what are some of the easy low-hanging fruits? And I think the one that we talked about earlier, where if I'm predicting something and then verifying it, there's low risk in that, right? I'm making a prediction and then I'm just verifying my prediction. And that gives me more confidence in the result, but it also gives me higher quality because now when I measure something, let's say that's really good, and it's not supposed to be really good, I'm not just going to pass that part. I'm going to perhaps bin it out. So I think there are a lot of opportunities that credibility of the machine learning, the understandability is not as important. It will be later, but I think there are a lot of opportunities where it's not so important just yet.
I do think that there's several applications which will benefit from it significantly. The other one, it's been presented in a bunch of papers in terms of pattern recognition for different kind of wafer effects or tests running with geographic information. I think you can come to some very interesting conclusions with a little bit more knowledge versus considering a test in isolation. So I think those ones are also apt for, immediate deployment. I remember there was some papers from NVIDIA where they mapped scan tests running on their devices, and then they turned it into an image recognition problem. But it was very interesting to see how they were applying one set of problems against a known set of machine learning algorithms. It's similar to, how we're leveraging high power statistics. It's how do I form the data to use this algorithm to solve a problem? Primary reason for that kind of approach. And I think several kinds of problems are really well suited to that. And then I think that there's the next set of problems about what other data is really going to be needed to get to a better insight.
you want to improve quality, right? So if we want to get to autonomous driving vehicles, then we have to drive towards zero defects. We used to talk about parts per million, then parts per billion, and now we are saying, no, there can't be any. We want to get to zero. And the only way that you can at least approach that asymptotically is by using machine learning. Let's say we have all this data that's coming off of all of these testers. And it's kind of funny. It's like we're looking for things that we know to look for, and we find them. But what we're not finding are the things that we don't know to look for. So it's the unknowns that where machine learning is really going to drive the value. Because let's say you have 10 important things that this data is telling you. Maybe we're finding 3 of them. Now, these 3 things might be the most important ones, but as a company or as a manufacturer, I sure do want to know what the other 7 are, especially if it's going to create a customer return or some sort of catastrophic failure in the future.
Yeah, I think what you're talking about is an ability for an institution to learn and get access to, it used to be fault models, right? So we went from pretty much every semiconductor company that was doing digital making their version of scan. And ultimately, there was the EDA industry that got formed that started to make tools and develop process to do stuff. I think machine learning and is kind of in that same spot back 20 years ago where the EDA industry was. And it's really, how do I get access to these more advanced relationships and learning of process, technology, topologies, and then applying it back to chips and making it easy? Because, your test and product engineers can't be an expert in everything. How do you quickly get to those insights becomes vitally important, where it doesn't need a machine learning expert. So how can we kind of cross companies and get that learning? It really can be independent of process technology, because I think the basic themes have been the same for these kinds of patterns. So there's real possibility here.
Let's talk about yield so there's a lot of value in yield understanding. And going back into the 90s, that wasn't generally the case. If I had to think about retrospectively why, I would say just we didn't have the volumes of data that were possible. And now we do. We have, once the mobility era hit and we were shipping billion phones a year, and now that data starts to be much more meaningful. Why is the yield understanding so important? Is it just because of there's so much data, or are there other things that we should be thinking about?
It used to be more of a black and white, this thing is working or not working. I think now there's more interfaces and blocks that require calibration. And then the question becomes, can I recover a number of parts off of a wafer? And by the way, if you compare that against test time reduction, it's way more effective in terms of profitability to recover a % of yield versus a % of test time. So it gets very interesting in terms of what does good really mean. And if you can continuously monitor that and make the perception from the customer that the product is working the same way, even with some tweaks in the background, because that's what a lot of these interfaces are doing anyways. I think that's where the real value is. You can get more good parts, reduce your scrap costs. So how do I optimize that?
I think what you're also saying is a lot of these structures, they build in after production calibration pieces that allow the product teams and let's say the manufacturing teams to tune that particular IP into the sweet zone or into spec. That's another area where machine learning during the test actually could help do that. It can predict what those tuning parameters are. Laser trim, for example, is one of those where you want to trim something, but you don't want to over trim because once you do, it's too late.
I think in the case of a laser trim, you're also trying to do a very coarse thing. And then as you're in situ, you want to be able to sort of adjust for its aging. You get yourself into the neighborhood, and then there's more soft repairs that can go on, will become more and more important.
So let's talk about the technology, deployment of it. Are we ready to scale? I mean, I see that this risk aversion and just the nature of our industry and the way that the supply chain is disaggregated and it's so complex. It's very hard to get, first of all, everyone to understand. Beyond that, every customer is a little bit different, and getting all of that connected into some sort of infrastructure is no trivial task. But to me, that's got to happen if we want to really and truly take advantage of what we're talking about, you have to have that infrastructure in place to move data around, to protect it, to utilize it throughout the supply chain. And models have to be smarter than they are today. Like you said, most models today are supervised. Eventually, someone has to come along and say, hey, we need to update that model. That's going to have to change, where the model is going to have to tell us when it needs to be updated, rather than we figure out that the model needs to be updated. So there's a tremendous amount of activity going on in the industry.
The good news is we're leveraging a lot of the pieces. It's not like we have to invent a new security model. We don't have to invent cloud computing. I think that there's a lot of base technologies throughout the industry that will enable us to get there. I think the other business motivation is, and this is talking to my own customers, is every one of them seems to have the goal of you need to be able to use machine learning at test because there's this value there. So there's definitely a corporate motivation that if you're not doing it now, you're going to be missing out and you're going to not have an advantage in the future. So I think the components are there. I think that the knowledge is there, and it's really getting all of these pieces together. And I do think from a data transmission standard point of view, it's also there. So I think we've got the right components now, and it's really a question of the companies that figure out how to combine these components and who to partner with will get an advantage over the next couple of years.
So you talked about your company, proteanTecs. proteanTecs is an Israeli-based company that deals with machine learning and AI. So give us the background on the company and why is it different from others in this category?
We are a data analytics machine learning company that's really focused on deep data for health and performance of systems. So we're really trying to figure out how to get the most performance out of your systems and how to, whether they're starting to age or whether you can tweak out that little bit of performance. Now, we were formed about in 2017. There was 3 founders of Mellanox formed this company, and it's really addressing problems at industry scale. So we're able to scale up using cloud computing, and we can also scale down using edge computing at a tester. Now we're silicon proven at multiple process nodes already, even though we're a 5-year-old company. And our primary markets are really data center, automotive, and recently announced communications. So, but what we've discovered through our product is really you need a multidisciplinary approach. So we have a lot of machine learning experts, but we also start all of this with design features. So we kind of have to combine all of those skills. So I should probably mention a little bit about what I mean by deep data. What it really comes back to is what are the process and technology features that are needed to understand the health of a system or a piece of silicon. So we've developed something called UCT, Universal Chip Telemetry. And that combined with focused machine learning algorithms has enabled us to drive new insights. And so as I mentioned, the models can run on edge and cloud, but it's really the combination of those 3 things, the deep data generated from our UCT, the machine learning algorithms, as well as the cloud or edge computing, all combining to give you this super understanding of the health and performance of your system. The starting point is that there are several kinds of IP that we can insert into your design. It's a combination of hard and soft IP. So we do a lot of simulations at the front end of the design process. And one example of a UCT agent is really our margin agent. So what we do is we look at all of your timing runs, and then we have a way to identify the critical paths. We give recommendations on those. And then we insert the soft IP that will say how much margin do you have on each of those. Now, what you can do with that gets kind of interesting, which is I can run it at wafer test, but I can also run it in the field. So I can keep track of it in the field. Oh, I had 30 picoseconds margin. Oh, it went down to 20 picoseconds. With that agent and using machine learning and using a reliability study, you can then predict at what point you'll have a failure. Now, we have all sorts of different kinds of agents. We have operational ones. We have ones on interconnect, ones that are for classification and profiling of process and technology. So there's lots of different kinds that we do insert into people's designs. And then it's really having that library of algorithms that you can run on top of those measurements. So, and our algorithms are really looking at multiple parameters as part of it.
Okay, so let's talk a little bit about the aging specifically for autonomous vehicles. When we think about autonomous vehicles, it's extremely important that these chips inside the vehicles actually can communicate to the vendors, to the suppliers about when they need maintenance or when there could potentially be a fault. If that's happening with our laptop, that's one thing. It crashes, no big deal. We buy a new laptop. But if that's happening with an automobile, then there's potentially a fatality or a catastrophic event. proteanTecs is working on some fascinating things there. What can you say about that?
Yeah, so the amount of content in a car has been increasing considerably. If I look at the car I have now versus the car I had just over 10 years ago, the number of microcontrollers and the amount of processing of data has exploded. And, from a user perspective, it's very exciting. I can do things like see the car go beside me and then I get a little warning light. But on the other hand, it does add a lot of complexity. And car companies are just getting used to this level of complexity. I'll tell you a story from about 10 years ago where a board went bad on my hybrid, and they just kept swapping boards on that car until they found the right one. So having the ability to say that this chip or this subsystem is going wrong is extremely valuable. And one of the technologies that we offer is really understanding the health of a system like that. So we'll be able to identify not only that a subsystem has gone bad, but where in that chip could be a aging or reliability problem going forward. And the really cool part is it could get you to predictive maintenance. So we'll be able to see sort of how that device is aging over time, and so that way you can bring it into the shop and basically get that component replaced.
For today, I think that's all we have time for. I want to say thank you for coming on the show and sharing your insights and experience with us, and looking forward to some future updates from you and proteanTecs.
Thank you, Keith.
To round out this week's episode, here's Junko's top 3. Hi, Junko.
Hi, Keith. So I'm sure you're noticing this too, but in-person events are slowly making a comeback. In fact, Advantest exhibited at Semicon West and Semicon Japan last December. So what I wanted to tell you today is how these shows went. So here we go. My first takeaway is about Semicon West 2021, which was held in San Francisco in December. The show traffic was much lower than previous years as expected, but customers who came to see us were so very happy to see us and very happy to have face-to-face conversations with us. In addition to the exhibition, Advantest presented multiple papers and moderated a panel discussion at Test Vision Symposium during Semicon West. So we were very busy. Then my second takeaway is about Semicon Japan, which was right after Semicon West. While the overall show attendance was down by about 50%, Advantest booth welcomed as many customers as previous years. Then again, our customers are so very happy to see us and learn about the latest test solutions. Speaking of the latest test solutions, my last takeaway is that we successfully showcased our latest test solutions at both Semicon West and Semicon Japan, including some new products like B93000 link scale, T5385 memory platform, T2000 IP Engine 4, and ACS, all of which support our mid and long-term strategy, Advantest Grand Design. So I hope you will continue to see us more at in-person events this year. As mentioned earlier in the news section, we will be in Scottsdale, Arizona in May for Voice, and we'll be at Semicon China in June, just to name a few. So I hope the listeners of Advantest Talk Semi podcast series will come and visit us. Back to you, Keith.
Thank you, Junko. Well, that does it for another episode of Advantest Talks Semi. See you next time.